Oh. Wait. Okay. Alright, so let's see. Light, UV, visible, etc. How chromophores work.
Wait,
Yeah?
okay, found it.
Mm-hmm.
Yeah. Like that stuff. This is all from my last practice test. Some of it like I kind of get, but
Mm-hmm.
light, I just um
Yeah.
yeah.
Okay, so like you've seen like the entire light spectrum
Yes.
image. Okay. And by the way, ultra means more than, and infra means less than. So infrared is going to be less than red, so it's going to be on, the left side of the visible spectrum. That's like Roy G. Biv. And ultraviolet is going to be on the right side, meaning it's going to be a higher frequency than the violet colored light.
Yeah, I can't like really remember exactly what the thing was. Probably should have been more specific, but um I think it was like the absorption versus like the reflection of
Yep.
them and
So
like the complementary stuff.
yeah, so there's a chromophore is essentially like it's like a pigment, and pigments and chromophores they have lots of pi conjugated double bonds. So so what does that mean? That means that there's a lot of resonance stabilization. So the usual like thing with let's say if we're just dealing with an atom, you like
Yeah,
shoot.
I get the
Yeah.
I'm good with resonance.
Oh no, I meant like for
Oh,
a regular atom, if you like shoot a photon at it and it's just the right energy, it's going to cause that an electron to go from a ground state to an excited state. And since the excited state is since the excited state is less stable, it's going to go back to the ground state, and when it goes back to the ground state, it's going to shoot a photon out at that same energy level. So that's just how it generally works. But for a chromophore, which has resonance stabilization, it's going to if you could shoot a photon at it at a higher energy level.
wait, you said
Yes.
when it goes down to the excited state, what did
Oh,
you say it releases?
like a photon of a equivalent wavelength.
Oh, okay. Yeah, there's some equation for that I was just doing before.
Maybe you're thinking about the work function.
Um, no.
Mm-hmm. Yeah.
Let me find it. No, let me find it. Hold on.
Okay.
Um,
But the idea with chromophores is since they are so resonance stabilized that if you shoot a photon at it at some energy level, it's going to be like the resonance stabilization is going to allow that molecule to go to a lower energy level. So when it shoots a photon out, that photon that it shoots out is going to be at a lower energy and therefore frequency.
wait,
Mm-hmm.
it allows it to go like lower than
Mm-hmm.
I thought the ground state was the lowest.
Oh, sorry. So that was just dealing with an atom by itself. But a chromophore is like a pigment, for example, which is a larger molecule filled with lots of pi, conjugated double bonds, and that gives it this type of, it gives it resonance stabilization. So it's going to lower the energy at which, so like, if you shoot blue light at it, for instance, it can emit, like, it'll absorb the blue light, which is a higher energy level than red light, but it can emit a photon that's red light.
Sorry, I was looking for this formula, but
Mm-hmm.
is it? Hold on. I'll make just Control F. It's way easier. Oh, never mind. I don't have it. I did it in my Anki tag, so it's like hard to find. I don't know. Whatever. I can look for it later. So it lowers the energy. Yeah, I get that. So you're saying.
Yeah.
Okay. Wait, can you say the light thing again? Sorry.
Sure. So here, let me go to your thing and I can write it down in. All right, Kristen.
You want me to open up?
This is content 3. Got it. Okay, so here we go. I'm gonna just copy and paste something like this. Wait.
Got it.
What's up?
Oh, I just said got it.
Got it?
Like I see it. Yeah.
Oh, the thing I just copied and pasted?
Yeah.
Okay, I guess it's not as slow as it usually is.
Yeah.
Yeah, so you see how all of these have tons and tons of conjugated pi double bonds?
Mm-hmm.
So essentially what basically happens is dragon's blood, weird. Okay. Yeah, so basically like, what happens, so like, first I guess I'll give an example of like an atom. So whatever. Nucleus. Electron. And let's say, we shoot some photon at it. This causes this to go to excited state.
Oh, got it.
All right, so this is just for an atom. So let's say, I shot a photon, HF, right? Energy of photon. So as it absorbs it.
Oh, that's the formula.
What formula?
The E equals HF or something like that over.
Yeah. Well, yeah, like the energy of a photon is HF. There's another thing called a work function. Did we talk about that? Okay. So, well, yeah, HF or HC over lambda.
Yeah, that's the other one.
Okay. So, yeah, so basically this photon, that's the energy HF. It gets absorbed, which causes that electron in the ground state to go up to an excited state. So that's where it is in that second version, the arrow, whatever. And then, as it goes down, oh, I don't know why it's not doing like the full thing, but I drew here like, another photon leaving. Yeah.
Got it.
Yeah, okay. So, yeah. So so it's the same, it's going to be the same energy level. It'll emit a photon at the same energy level is what I mean.
Okay. Got that.
So this is for atoms. Now, for chromophores, so for these, like pigments basically, whatever, I'll just choose one that's like, or I'll just write whatever, chromophore. Do you see that now? Okay. So for these pigments, right? Let's say that we shoot, a photon, let's say it's blue, at the chromophore. Chromophore has resonance stabilization, which lowers the energy level of it. So now when it emits a photon, I made it red because it's a lower energy
Oh, I see.
photon.
I see.
Mm-hmm.
So the photon it emits will be lower than the one it absorbed.
Mm-hmm.
Got it. Yeah, I know there's like a weird passage on this.
Is it about lobster stuff?
Yeah.
Okay. Yeah, I have another student that was doing Kaplan, and yeah, I saw that passage.
Yeah, and that's like where this one came from.
Yeah, so they
This
have
bullet.
something they call it the subtraction color, I think, or something like that.
Yeah, like is that something that I need to know, kind of, or like not really?
Um, so in that like chart or whatever that says the like color and the subtraction color, that is just an example because the color that they first show is higher energy than the subtracted color, which is what comes out.
Yeah, I guess I don't really get like a lot of the light stuff.
Yeah. Do you have that passage open or?
No, I have no idea what even test that's in. I remember I took that like a while ago.
Okay, I can look back at. Let's see.
But I just remember like even when I read the explanations, like a lot of the concepts for the lights were like, that's why I had no idea what's going on, just because like I didn't review that yet.
Yeah.
So
Okay, let me see something. Oh wait, it's saved somewhere else. One sec. Hypothesis is talking about the
basically.
Okay. I got it. Yeah, so they're saying wavelength, color, subtraction color, like blue, orange. So, and then it says here. Let's see if I can. Screenshot this.
I mean, if like the subtraction color is not really important, I don't really need to go over that passage because I think it's more just like conceptual than the specifics more so.
Yeah, I added it to the notebook. So basically, they're saying that conjugated double bond systems stabilize the electrons, so they can be excited by lower frequency photons with wavelengths in the visible spectrum. So such a pigment, also known as a chromophore, can then transmit the subtraction color, which is a color complementary to the one absorbed. So the example they give is carotene. So that has 11.
Yeah.
Yeah.
But is like, I guess what I'm asking is like, do I need to know like subtraction colors and stuff, or like no?
Well,
Or is that just like something that's supposed to be new from this passage? Because I know sometimes like they just give you new stuff. Or
well,
is that something I'm supposed to
it would be
know
good to
about?
know like the complementary colors.
Okay.
Yeah, I can draw out how to do them. So let's see. That wasn't that good. Let's see.
Because yeah.
Hold on. I'm gonna redo this.
I can look at that later if you want.
Okay. It's just the complementary colors, but yeah. What was your? So what were you saying? Sorry.
I actually don't even remember.
Okay. Let's see how chromophores work. So okay, that's how chromophores work.
Yeah, I guess I just wasn't like really sure about that, but I'll just look at the concepts then. Like I'll watch a video or something.
Got it.
The
All right.
nucleation. I have no idea what that is,
Uh-huh.
honestly.
So I believe nucleation is like when something when you're like mixing something or something, it will make like bubbles, and to start a crystal. Let's see.
Is this like I feel like I don't even remember where this could have been, like where this could have been, like what chapter or anything.
Yeah.
So it's not even something I could have like looked in one of the books.
Yeah. It's yeah, it's related to like crystallization basically. So let's see. So when you try to make a crystal, right? Nucleation is the essentially like the first step where the solute molecules or atoms that are dispersed in the solvent start to gather into clusters. So I remember there's a question that said, "What's the reason for adding something?" I think it wasn't a boiling chip, but it was something.
Yeah, I have no idea. So I could look at that later too.
Okay.
Then mitosis. I like looked at mitosis and everything. Like I read that in the book, but
Yeah.
I guess for like the microtubules and like the spindles and all that stuff forms, like I
Mm-hmm.
have no idea
Okay.
because it doesn't talk about that like as specifically in the books. It talks more about like the bigger picture of it, I guess.
Yeah. In one of my Anki cards, they talk about these. Let me see if I can find it. Like I talk about actin and stuff, and microtubules and intermediate filaments.
Okay, so
But yeah, microtubules basically make like the like portions of the cytoskeleton where things can. I'm gonna have to do like a custom study thing. Study increase today's. Or wait, what? Sorry. Review ahead of whatever 100 days.
hmm?
Oh, nothing. I'm just looking for
Oh,
it in
if you
my.
want, I could look at that one later too.
Okay.
Is there one that's like better to go over now then
Mm-hmm.
that you see on the list?
Yeah. Well, I see mitosis and meiosis. So, what do you like? Yeah. What about meiosis?
Like, yeah, like what I was just saying about the microtube, like that stuff.
Okay. Yeah, meiosis.
Um,
Has like part one and part two, where part two is essentially the same as mitosis.
yeah, I remember that.
And then let's see, KSP stuff. Okay, what are your thoughts or questions about that?
Um, just like in general, like when like it's the I know you don't count like the
Like solids
gases.
or yeah.
What'd you say?
Oh, like solids, pure liquids, only
Yeah,
aqueous stuff.
but then it's like when I guess the equation and then when it's larger, like when the precipitate forms and stuff, I think that's what I got wrong on that one.
Okay. KSB. So basically, if a precipitate forms, it's no longer soluble, right?
Yeah.
I had a section here where yeah, solubility. It's in
In my
content two
notebook.
with not a Roman numeral, just content two number, and then there's solubility. So
Okay.
KSP is an example. It's called the solubility product, and you get that from the balanced.
Wait, we use no, it's no liquids and solids, right?
Yeah,
Here.
it's basically just aqueous stuff.
Oh, so no pure gases and solids.
Yeah.
Wait, no gas. Or no, that doesn't sound right.
Oh yeah, just aqueous stuff.
But what do you like? I know there's certain things you don't use.
Mm-hmm.
You know what
Yeah,
those
you
are?
don't use anything unless it's aqueous. because solubility is basically something that is soluble in water or something. So you're
So
just gonna have
you can use
aqueous.
pure liquids.
No, just since it's something that's
So
soluble in water, right? It'll be aqueous. Like
so
pure.
no. So like what I'm saying though, you
Hmm?
don't use pure liquids then. Like what?
You don't use anything unless it's aqueous. Because
Okay.
aqueous means it's already basically dissolved in water, right?
Mm.
Yeah. So there's molar solubility and there's solubility product. Solubility product you get from the balanced reaction equation, and it's basically just an equilibrium like constant, just like you would use like law of mass action. Since solubility reactions start off as like a solid.
Wait, hold
Yep.
on. Okay, sorry. I couldn't find. I'm where you are now.
Okay. Yeah, since they start off with solids, you're not going to, and you don't use the solids, you're not going to really have a denominator in this case.
In what case? I don't know where. Like, I have
Oh,
the page you're on, but like, where are you looking?
just so you see like solubility reaction, KSP expression, KSP
Oh, like the
calculation.
top part, the black part?
Yeah. But
Okay.
this I haven't like written down. But if you can see like in the solubility reactions in the top part on
Oh,
the
okay,
left,
okay. We're just looking at the. Okay.
yeah. So see how they all start off as like a solid. So you're not going to include those, so you wouldn't have a denominator because normally like the denominator would be reactants.
Yeah.
So yeah, so that's something. The KSB is something that you get from the balanced reaction. Molar solubility, on the other hand, you get that's experimentally established, and basically that's like the maximum salt concentration that you need to solvate in an aqueous solution. So the example I gave was lead iodide, I suppose, and it turns into like lead, ion and iodide ion, and then I wrote that out. I wrote the KSB expression out. It's the concentration of the Pb2 plus multiplied by the concentration of the iodide, but to the second power.
Um, so you have to use the molar solubility experimentally, and then
Yeah. So for
the
instance, if they,
solubility product is the KSP.
correct, yeah. So basically, if they gave you like concentration, like a value for concentration of like lead or something, then you would do like the actual calculation. Because see, so I wrote that's the KSP expression, and the KSP calculation would be 4x cubed.
Wait, what?
Oh, so do you see how like the KSP expression in that second column?
Yes.
Um, yeah. So it's going to be like the second row, the example that I used with the PBI2.
Um, okay, but how are you getting that? Like, how are you like, I see that you're
Oh,
getting,
so it
okay,
all
so the
comes.
PBIC.
Yeah, so it all comes
So
from something called the
you're
law of
looking
mass.
at,
Yeah.
wait, you're looking at the second row, not the
Yeah.
second to left. Oh, but it's the same thing either way. Okay. Um, yeah, how do you even get that though?
Okay, so that this all comes from this. So every capital K thing, whether it's equilibrium, whether it's Ka, Kb, Ksp, Kw, they all come from something called a law of mass action. Oops. Here, I'm writing it out for you. All right, let me sync it.
Got it.
All right, yeah, do you see where I wrote law of mass action?
Mm-hmm.
All right, so basically this is just, for like the reactants like are capital A, capital B, and little a and little b are just like the numbers in front of them, like the coefficients.
Those
Yeah.
are the okay. So, like the capitals are like whatever the atom and whatever is, and then the lowercase is like the coefficient, the number.
Mm-hmm. Yeah, and
Okay.
then if you want to turn it into some K, right? You put the products on the top, reactants on the bottom, and whatever the coefficients are, you use as exponents.
Okay.
So in the example that I wrote in light blue with the iron iodide,
Yes.
do you see how the coefficient of the iodide ion is a 2?
So it would be I squared.
Exactly.
So then you're looking at that, and then but in the chart you have in black is the second one and the second to last thing. And either way, it's like the same thing, so it doesn't really matter, I guess, right? Yeah.
Oh
Actually,
wait.
yeah, no, it is.
Oh, and the second to
Never
last.
mind.
Oh yeah. It just
Like
like
reverse, yeah.
different kind of like order, I suppose. Like it's the different reactant
Yeah,
that's doing
yeah.
it. Yeah.
Okay. So then you get 4x cubed. That makes sense. And
Mm-hmm.
then what do you like? How could you calculate the? Oh, so it would be KSP equals 4x3, and then you just solve for KSP for x using that
Yeah.
then.
So when it comes to so basically for molar solubility, right? They'll give you a value for x, or rather, they'll give you a value maybe for like the concentration of iodide, something like that. And then you would incorporate
Um,
that into the
Wait, they'll give
4x.
you a value for the concentration. How would the concentration help?
Oh, so that's okay. So all right.
Oh,
Let's
because
say that they
those,
give you a KSP value.
if they give you a KSP value?
Yeah, then you can set it equal to the 4x cubed,
Yeah.
and then you can solve for the x. And then you can solve when you solve for the x, then you can solve for how much like PB there is and how much iodide there is because
Oh,
you
wait.
plug yeah.
Yeah, wait. Obviously, because the brackets are the concentration, so
Mm-hmm.
yeah,
Yeah.
that makes sense
So
now.
if they gave you a KSP value, right, for the example that I have here with that's in light blue, you would set it equal to the 4x cubed, right? And then you'd solve for x, and then if they want you to if they want you to figure out the concentration of the lead ion and the iodide ion, once you obtain x, then the regular x will be the lead ion concentration, and that you'd plug
Squared.
in the x into the 2x squared thing to get the
Oh,
iodide
into the
ion
2x
concentration.
squared.
Yeah.
Wait, why is that?
Mm-hmm.
Why is it 2? X squared.
Oh, because you put
I
it
get the squared.
into
I
yeah,
just don't
yeah.
get the 2.
Oh, you put it into you put it as a coefficient as well in the
Oh,
calculation.
so if you have an exponent, you also keep the coefficient.
Mm-hmm. Yeah.
Okay.
Yeah, that's for the calculation. Um so yeah, like if they give you a value of KSP, then you're going to be doing that calculation, and X is just going to be, I mean, X, yes, is going to be experimentally established. And if they give you a KSP value, like, that's going to be experimentally established as well.
Okay. So yeah, you can figure that out then. I
Mm-hmm.
see that. And
Okay.
then it's pretty much like the same for the KW, the KB, the KA, like all that's like the same, right?
Yep.
Okay. Good to know.
Yeah, and then I found
Uh,
the thing about that I wrote my Anki deck in my Anki deck about microfilaments and stuff like that, microtubules.
yeah, like I get what they are, I
Mm-hmm.
guess. The things that I get confused with what they are is like all the things that start with the C in the beginning, like the chromatin, centromere, all that stuff. But
Mm-hmm.
that's just like besides chromatids, all that stuff. But that I can figure out. That
Mm-hmm.
I just need to like look at a little bit more.
Yeah. So I basically wrote microtubules,
Actually,
right?
let me get that.
They're so like in the context of like all the C stuff that you mentioned. So okay, yeah, it came up on the thing for content 3, Roman numeral 3. Um
Oh,
yeah.
content 3. Yeah, because I
Mhm.
remember like I read the book, and even when I was like trying to figure out the question I got wrong, I like looked in the book for the answer, and it doesn't talk really much about like where the microtubules are formed and stuff like that. It just talks more about like what the chromatids or something are doing.
Okay.
Um,
Yeah, so they're basically going to be the things that they're kind of like these like kind of tubes that like kinesins and dinins, those like guys.
the motor proteins.
Mm-hmm. Yeah, they move along that. So basically, like, there's like a positive end that grows towards the periphery, which is like away from the nucleus, like out towards the cell membrane.
Wait, I'm gonna try and get a picture.
Mm-hmm.
Um, let's like look at it. I maybe I have a picture. Yeah, I think this will work. Actually, no, because this doesn't really help because I have no idea where the microfilaments are.
Oh yeah, those are things like actin and stuff. You'll see them in like muscle contraction,
Yeah,
but
but I
it
can't
within this, yeah.
like the picture of like the mitosis, how it does all the stuff. It
Yeah.
shows you all the
Mm-hmm.
steps. Where are like the microtubules in there? Like I see the sister chromatids. Are they? That's the spindle. I don't. Are the microtubules like this
Mm-hmm.
dotted thing? Like I have no idea what they are.
Yeah. Here, let
What
me.
what they're like shown as.
Yeah, let me get like a nice picture for you. They're basically, yeah, they're parts of the cytoskeleton that are attached to the centriole, and they can pull. They're the things that pull the sister chromatids apart in anaphase.
Attached to the centriole. I can share with you the Kaplan book picture, unless you want to
Yeah,
unless
sure.
you know what you're looking for, kind of.
You could do that.
This is the the picture that I was just looking at of all the stuff. Are these where the heck are the microtubules?
Yeah, those will be it.
Oh, these dotted lines?
Yeah, I was trying to find like a more
Yeah, I know the picture
detailed
kind of
one.
is
Let me see.
not great. And then this I don't even know.
The
I
spindle
guess
apparatus.
yeah, I mean I see it's like this, I guess, but then this is just the spindle. So then the apparatus is that when the microtubules are into it?
Yeah, they anchor onto that.
Okay.
So it's responsible for like movement within the cell.
The spindles?
The the micro tubules. The
The
spindles are
microtubules
kind
or
of
filaments?
what they're attached to.
Wait.
Yeah, what's up?
Oh, never mind. Never mind. I thought
Mm-hmm.
for a second I thought we said microfilaments, but never mind.
Oh yeah.
Okay, cool.
Here, I'm trying to find.
Um, yeah, because I know the question wasn't even what are what's happening here, like prophase one or the recombination, whatever. It was where are the sister, no, where are the microtubules, or no, where would the thing arrest if the microtubules are not formed? I was like, I don't even know. I literally have no idea. And
Oh,
I couldn't even think.
I mean, wouldn't it would be either
Well, I don't know where they're
metaphase or
formed.
anaphase.
Yeah,
Yeah.
I don't know where they're formed. That's the issue. It doesn't even tell me in the book.
Okay.
I looked. It doesn't say it. I watched their video that it gives you. It
Mm-hmm.
doesn't talk about that at all. Just talks about kinetochores.
Yeah.
I don't
They're
know what
like
that
these
is.
like cute little guys that like walk along the ends.
The
Like
kinetochores?
can you oh no, wait, I'm thinking of connections, my
Oh,
bad.
yeah. Wait. What?
Yeah,
Who
no,
is
the
walking?
kinetochores are the things that are around the they're basically attached to the thing that's in the middle of the chromosomes.
The the centriole or centromere. What is it called again?
Oh, centromere.
Yeah,
Yeah.
centromere. See, they all start with a C or a
Yeah,
K.
yeah.
So
I see what
annoying.
you're saying.
I get the chromatin, I know is less condensed chromosome. Centromere. Usually I know that. I'm upset about that. Um, the kinetochore, I don't even know what that is though. But who's the guy that's walking that we were talking
Oh,
about?
kinesins and dyneins.
Oh yeah, the motor proteins. All I know is that they're motor proteins.
Oh
I'm not
yeah,
too sure much else.
they travel along um the microtubules.
And what does that do for us?
Oh, here I found a great picture.
Why do we care that they travel along there?
Oh, because like I guess if they ever ask you things about like if like whatever the direction of something that moves it, I think kinesins move it towards, let's see, along the periphery, dyneins towards the nucleus.
Hmm.
Yeah, so let's see. Do you see the image I just
Wait, I don't
added?
see your screen.
What's up?
I don't see your screen.
Oh yeah, I haven't been sharing
Oh,
my
I thought you
screen.
were showing me a picture. Oh, you uploaded it somewhere?
Yeah,
Where is it? Oh, okay. Oh,
yeah.
well, I have to zoom out. This is very big. Okay, got it.
Yeah, so this is basically the entire cytoskeleton. So you get to see the microtubules. They're those like really. They're the hollow. They're the
Are they the
large
red things?
hollow. Yeah, it's like a like I don't know like what kind of color is that? Like a bronzish kind of color. But yeah, they're the hollow tubes that are pretty thick.
Wait,
Yep.
I didn't think actin and was a microtubule though.
Oh yeah, it's not.
Oh, okay. I
Actin
thought
makes
before you said it was the
the
microfilaments.
microfilaments.
And those have nothing to do with the mitosis.
Um, well about mitosis. Well, they have so everything here has something to do with the cytoskeleton. So microfilaments, like they can assist in. Well, we know that they're important in muscle contraction, but they're also going to
Yes.
assist in intracellular transport and trafficking, cytokinesis, right, and the cell shape. So the micro,
Okay.
so the let's see.
Oh, so I guess they are important in mitosis because cytokinesis.
Yeah, yeah. Um, so where are they? I mean, I see the intermediate filaments. Oh,
Oh,
the
are you looking at
microfilaments
them
are. Wait, are these
up top?
brown? Yeah, they're small. Yeah, they're like these brown,
Yeah,
like
I see
kind of
them.
thin things. So that makes sense because they're they work in terms of the villi, and that's what's on that top over there, the microvilli.
Okay. But I guess the thing I got wrong back to that is like I have no idea where these microtubules are formed. Like what they look like in like the picture of the mitosis,
Okay,
and that's what I got. Like
yeah.
I forget what they are,
So you
but
see, the.
it was asking where. I wish I just screenshotted this
Mhm.
question, but um,
You see that where the
it was a while
centrosome
ago.
is in the picture?
Mm, yes.
It's like in that center.
Wait, where is it pointing to? Oh, okay, yeah.
Yeah. So
Oh, what is the centrosome like? What is that in like in the
that's where the microtubules like start from.
sorry, it's all this stupid pop.
Mhm.
Um, that's the centrosome. Okay,
Mhm.
where the microtubules start from.
Yeah.
But the centrosome is there in interphase, and then it goes away. No.
Oh, so okay. So when you start to so we can see that it starts from like a centrosome, right? And then there's an end that's towards the nucleus, and there's an end that's towards like the periphery, or aka like the ends of the cell.
Oh yeah.
Mm-hmm.
Okay, I'm confused. Is this like any? Is this picture though anything to do with mitosis, or just the cytoskeleton?
Oh, the cytoskeleton. But I'm gonna use that to talk about mitosis, because when
Okay.
you have mitosis, right, you're going to basically have things go on opposite ends. So if you can imagine, so you see how it originates at the centrosomes, but
Yeah.
now imagine like the centrosomes being like instead of it, because in the picture there it's like in the center, but in mitosis, right, they're going to be at opposite ends. So it would be like,
Wait, what's going to be at opposite ends?
oh, the centrosomes.
See, the thing is, in my picture, there's no centrosomes anymore. They go away.
Um,
Are we sure they're at different? I don't, because I mean, maybe they don't show them, but I don't like see, like I see them in the beginning and then I see them at the end, but I don't see them Like I see them after cytokinesis, but I don't see them anywhere else, like during prophase, metaphase, anaphase, or telophase.
Yeah. Oh, okay. Because they get called centrioles.
What do they get called?
Oh, centrioles.
Well, in the beginning picture, I see centrosome and centriole.
Let me see.
The picture, or
Oh, wait. Centrosome. All right. Where do you see centriole? Is it in
oh,
the?
I'm like looking at like my picture because
Oh yeah.
now I'm very confused.
Mm-hmm.
Where did it go? Oh, here it is. Do you want me to share it?
Sure.
Okay. Like I see centrosome, centriole.
Yeah. So the centrosome is the overall thing that has those two things in it,
Yeah, I see that, but
and those two
then
things are the centrioles.
yes, I
So the
understand that,
yeah.
but I don't
Mm-hmm.
see like where do they go? Like I don't see them in prophase, I don't see them in metaphase, I don't
Oh,
see them
they
in anaphase, I don't see them
basically.
in telophase.
So yeah, it basically dissolves, and then the centrioles within them go to the opposite ends.
Okay, so the centrosome dissolves, but we still have the centrosome,
The centrioles
the
inside of them.
centriole.
Mm-hmm.
Okay, interesting.
Mm-hmm.
And then that's when they form the spindle fibers.
Yeah.
So the spindle fibers form during prophase.
Um. Well, wait. Yes. Yeah. In prophase, basically the nuclear envelope breaks down, the chromosomes condense, and basically the centrosome. It doesn't necessarily. It doesn't. I'm not. I don't know why it's not saying. Let me see something.
Yeah,
And
it's like
yeah, it seems
weird.
like
Some of
they
them
get
say
they basically migrate to the opposite ends of the pole.
the centrioles.
Yeah.
Chromosomes. Okay, because I don't even know what's going on. The nuclear envelope dissolves. The chromosomes condense. The centrosome disappears, dissolves.
Yes. Yes. Mm-hmm.
And then, oh, wait, I have notes on this somewhere.
Mm-hmm.
I just couldn't find them. Because I thought I got the big picture, but then it was asking me all these crazy,
Mm-hmm.
when is the microtubule gonna arrest? I had no idea what was going on. Okay. So mitosis, prophase. So then here's where the spindle fibers come. The sister chromatids is formed in interphase.
Mm-hmm.
Okay, this is so confusing to me. And I learned this 100 times. Okay, so then you're saying the spindles form from the so then metaphase happens. The chromosomes, yeah, I get the big picture. Like I get they go to the middle. Wait, what is this kinetochore doing again?
Oh, it's just the So centrosome is like the thing. It's like the almost like a membrane that contains the centrioles, and
Mm-hmm.
then in prophase it whatever dissolves, and the centrioles get to move to the opposite ends of the cell, and they release spindle fibers, aka which are made out of microtubules. Um,
Oh, the spindle fibers are made from microtubules. So then
Yeah.
technically, are microtubules formed when the spindles are formed?
Oh yeah, because they're made of microtubules.
Yes.
Yeah.
Or is that like a different like thing? Because like that's like where I'm still so confused. I'm looking straight at my notes. I had the textbook in front of me. I
Mm-hmm.
still have no idea where the microtubules are formed.
Oh yeah, yeah. So you could see that they're all already there before any type of mitosis happens.
Where are we looking?
Oh, in that big like picture of that cell, and
Wait, the picture of the self that you have is before any mitosis?
correct, yeah. Because they're
Oh,
always there because that's where
I
that's how
didn't
things
know
get
that.
transported like across this to different parts of the
The
cell.
microtubule, yeah, because we have
Yeah.
the two little
Um.
thingies on them.
So basically, yes. So there's a so when the centrosome essentially breaks down, the centrioles move to the opposite ends of the cell,
Yes, got that.
and then they grow.
I'm
They
with you
cause
there.
something called a MTOC, microtubule organizing center, and that's when they create the microtubules that form that spindle apparatus.
Okay, so this is all in prophase.
Um,
Like that's like
I,
where I'm
I,
still confused.
I think so. Yeah, yeah. In prophase.
Because it was asking me like where it's gonna arrest. Like I followed you all the way. I just
Yeah.
have no idea what phase we're forming these microtubules or any of that.
I think it starts like in prophase, right? Let me see. Okay. See, prophase, chromosomes condense, nuclear envelope breaks down, spindle fibers grow from
It
centrioles.
doesn't say.
So
Yeah,
they
it
do
just doesn't
start in
say anything
prophase.
about. Oh, so you're just whenever the spindles are there, like the microtubules you're saying are there.
Yeah, yeah. We call it yeah, we call them spindle fibers because they're kind of it's kind of like a spindle, and those things come out and they attach to like the kinetochores, which are just these kind of like proteins that are around the centromeres of the chromosomes, and
Okay,
so
I have a
they get
question.
pulled, so it's kind of like a spindle.
All right, so I think I follow. I don't know why this mitosis is taking, and I looked at this so many times, but so back to this picture.
Mm-hmm.
Is this are these dotted lines? Now I'm confused. Are they thinking like when I'm reading the description in the textbook, like I want to say that these are the kinetochore, whatever they are, but are they the microtubules then? Like I'm still confused now because
Okay, so here. Um. So here, check this out. So
like I feel like I can only get like the bigger picture of what's happening, like the sister chromosomes align at the plate, but I don't get like the small stuff. Or you're drawing in the content 3 Roman numeral. Oh
mm-hmm.
wait, you put something else in here. Is this is the picture that you put in? Is that what you want me to look at?
Yeah, I put in a picture that goes over like the different parts of mitosis, and then
Got it.
I drew something, so I'm gonna sync that so it comes up.
Okay. Centromeres. Oh my god, everything starts with the C. Okay, so I think where I went wrong was I just didn't know that where the
Yeah, do you see?
spindle was.
I
I don't
drew
see what you
something.
drew yet, but hold on, let me maybe zoom out.
Mm-hmm.
Oh, yeah, I do. The what is? Oh, prophase centrosomes is Is that centrosomes dissolve?
Yeah, sorry.
Wait, centrosomes. What does it say? Dissolve?
Dissolve, releasing centrioles, which migrate to the opposite ends, and those centrioles release
Oh, okay.
microtubules, which become spindle apparatus. And then I didn't finish that drawing underneath, but those are the centrioles. And then underneath I drew the difference between a centromere and a kinetochore.
Wait, so the kinetochore is like I get the centromeres in the middle. It like connects the sister chromatids, but the kinetochore is then like encompasses however you say it, the centromere and part of the sister chromatid. What is
Oh,
that?
sorry. So the centromere is essentially just the center of the
Yeah, I get the
chromosome.
centromere. I
The
know what that is.
kinetochore is this thing that wraps around it, and that is what the spindle apparatus attaches to.
Oh, okay, yeah. These videos are not very clear about that. Wraps around
Yeah, it's the thing that the spindle fiber is attached to, essentially. Here, I'm gonna throw in another picture here. Wait, what?
Wait, why could they not just attach to the...
Here.
I thought I read that they attached the centrum. Yeah, whatever.
Yeah, I added another picture. See if that comes up.
Oh, yep, got it. Okay. The kinetochore, yeah, orange. And then... Wait, what is this pulling force thing on the bottom that we're looking at? And what's this minus divided by 2?
Oh yeah, don't worry about that.
Do we care about that? Oh,
Nah.
okay. And do we care about these forces?
Oh, so these are. So hold on. So
So spindles are microtubules. That's just something I should know.
So those green things that are attached to the kinetochore, that is the spindle fibers, the microtubule spindle fibers.
Not the neon green, like the green.
Yeah, forget the inner and outer ones. But they're essentially the kinetochores are the proteins that attach to the centromeres, essentially, and the spindle fibers attach to the kinetochores. So
okay, that is very helpful.
Sometimes people don't in the diagram that you have, and even in the one that I copied or took a screenshot of from a textbook, says that they attach to the centromeres, but they technically attach to the kinetochore.
That is very helpful. Actually, because I some of them there's so many random words that they make no sense to me. But that does help. Now, do we get rid of the sister? Not the sister. Oh gosh. Do we get rid of the spindles? It doesn't look like it, but I thought we did. Or no, we get rid of the microtubules.
Oh yeah, think of them as the same. The spindle fibers are made of microtubules.
Spindle fibers are made of microtubules.
So you know what a spindle is, right? Generally, it's kind of if you're knitting or something, or sewing.
I get what you're saying, but I think then what I'm saying is
Yep.
What exactly are these dashed lines then?
Oh, those are the spindles, the spindle fibers.
Oh, but then the dash line's the same thing that does this.
Yeah, it's basically that's supposed to be. So I don't know why they use dashed lines, because if you look at the top, there's completely closed line, or for the nuclear membrane, right? And then
wait, I actually get it now. Yeah.
Since the nuclear membrane is breaking down, it's a dashed line, but So that's
I
why
think
they did it first, but then
yeah.
it doesn't really make sense for them to use the dashed line for the spindle fibers.
Okay, that does make sense because now in the picture I see they're connecting at the Canada shore.
Yeah. So basically they, in prophase they start, right? In metaphase they go, to the opposite ends. Or sorry, prophase they start to go to the opposite ends, and you know, in metaphase they attach to the kinetocores of the chromosomes that are along that midline. And then in anaphase they work like a spindle, like they you know twist or whatever, and they bring the things like back. They pull the
Pull
spindle
them
fibers
apart.
back.
Yes, yes, yes.
Yeah, and so after anaphase, right? It's the spindle apparatus has done its thing, and
So
so
it
they
goes
can go
away.
back to sorry, they can go back to being inside of the centrosome.
Okay. I think I get it now. I think all these like random terms
Mm-hmm.
just weren't completely clear to me.
Mm-hmm.
And the videos don't really help.
Mm-hmm.
Um, so I'm good with mitosis. Meiosis, I don't really care about right now.
Okay.
Yeah, because mitosis, it's going to be the same. Meiosis is like the same issue, so then that's just going to help me with that. So I don't really need to deal with that.
Yeah.
Optics, I don't even know what I meant by that at all. Did I just look at I think I just looked in the physics thing and just saw a chapter. I had no idea what it meant.
Yeah. Did that Reddit post that I did on optics help? Did I ever send that to you?
Um, did you send me that? I have no. If you did, I didn't see it.
Okay.
Sometimes I'm bad at checking my emails though, so that doesn't mean that you
Here.
didn't send it at
Here, I
all.
sent it in this chat right here.
Okay, let me. So then I can look at this later. Because I have no idea what I mean by optics. Oh wait, I just watched a video on this. Oh, I feel like a lot of this is like memorization. Am I wrong? Like
Yeah, there's a
probably
pattern you
not.
can think. Because, so I basically wrote this table down, and I remember, like, before, during maybe, the tutorial aspect or whatever, whenever they give you, 15 minutes before the exam starts, I would write that down on the paper that they give you for reference.
Oh, because this is like a high yield, it says in here.
Oh, yeah, definitely. So, yeah, you can memorize this table, but you know, I also underneath that basically explain what happens, like the pattern. So I write basically that diverging optical devices will always produce SUV, which is smaller upright virtual image.
Wait,
Yep.
where are you looking?
Oh,
Okay,
in
yeah. So
what I sent you.
that's
Yeah.
I watched a video. I have notes on all this.
Mm-hmm.
So but it's like it again. It goes in one ear, one out, and out another because I feel like it is mostly memory. Like I feel like I have to memorize this. Is there like
Oh yeah.
other than this
Yeah.
tape? Like it's just
This is
I
the pattern
guess.
basically. So basically diverging optical devices, right, whether they're lenses or mirrors, they'll always produce a smaller upright virtual image. Now,
Yeah, I kind of remember that.
virtual images are always going to be upright.
Wait,
And
hold on.
yeah.
Let me just look at.
Mm-hmm.
Let me just pull up my notes on this so I can like
Mm-hmm.
ask if I had any questions. Um, what would this be called? Optics,
Mm-hmm.
mirrors,
Yeah.
mirrors, I guess, right?
Or just optics. You can try that link that I sent you.
No, of course I would never have called it optics. That would have made too much sense. I probably called it mirrors. I called it reflection.
Mm-hmm. All right.
Okay. I don't know. Actually, yeah, I guess.
Okay.
Did I? Okay. There was a question on here.
Mm-hmm.
Oh, lenses and mirrors. Okay. So, hold on. I actually can't even look at this right now. This is crazy. Why did I do my notes like this? Oh, the convex. The convex mirror is like different than the convex lens or something. And then
Yeah, they're vice versa.
those are always reduced, upright, and virtual. I have the convex.
Yeah, so I'm going to copy and paste the thing that's on that Reddit post that I made.
Why did I even write lights and optics? I guess I have to. So I'm taking a practice test tomorrow, which I'm sure I told you. I guess I have to be more specific when I write what the hell I want to go over because I don't even really understand half of these notes looking at them. Oh, wait. Okay, there's a couple of things I know I do have to go over though.
Yeah, see like the latest thing that I put down for you in that notebook? Like underneath the mitosis stuff?
Up underneath me. Hold on.
Yeah, I'll be right back.
Yeah, I see it.
Hey.
Okay. Hello.
Hi. So do you see that in your notebook, the optics thing?
Yes.
Okay, so there's that table, but I also basically explain like the pattern underneath. So basically, a diverging optical device, whether it's a mirror or a lens, it will always produce a smaller upright virtual image. Now, for converging optical devices, it's going to change depending on the object distance. So, if the object distance is at infinity, it's going to produce
Wait.
yeah.
The virtual image is just behind, like it's like behind the thing, right? Okay. So this is where I get confused, I think. I just need to realize it's convex in mirrors and concave in lenses. How did they do that? Okay. So I get the diverging.
Yeah.
Lenses.
Now, for converging optical devices, it will produce ever increasing inverted real images. So as an object,
What is the ever?
So that's as an object gets closer. So when the object distance is infinity, right? It's going to produce a tiny inverted real image. Okay? So virtual images will always be upright. Real images will always be inverted, okay?
Yeah, I remember that.
All right, now...
UVIR.
Yeah, and then as we move that object closer, it's going to start getting larger in size. So, if the object distance is greater than twice the focal length, it's going to produce a small inverted real image.
So, wait, you have one.
Mm-hmm. Yeah.
You're always. So, converging is always inverted real. But then at the bottom, it's not.
Correct. So, it starts off like super tiny, inverted and real. Then, as it gets closer, it'll just be small, inverted and real. That's when it's...
Well, it starts off, but like it starts off, so when the object distance is infinity away, and then the I is the image distance, and the F is the focal length.
Mm-hmm.
When those are equal to each other. Oh, I drew these all out somewhere.
Yeah.
I drew them out. It just, my drawing doesn't really make sense.
Yeah, the drawing stuff for optics are really
stupid,
annoying. So I just use this, and so basically the idea is as it gets closer, right? So like, you know, if it's if the object distance is greater than twice the focal length, it's small inverted real. When the object distance is equal to twice the focal length, it's...
I guess what I'm confused about is I get that you're reading like the left side, but then like the object distance column, but then what about this image distance column?
Oh, okay. I mean...
Like, do they have to both be true? Like, because I get the left.
Mm-hmm. Yeah, you can kind of see a pattern here. Like, for instance, object distance infinity will mean the image distance is at the focal length. And when the object distance is at the focal length, the image distance is at infinity, right?
When the object distance is at the focal length.
Yep. Then the image distance is at infinity, right?
Oh, so there's no image because it's just so far away? Like...
Well, that'll produce no image. So, okay. So, like here's like another pattern here. So you see how object distance infinity, image is at focal length? And then object distance at focal length, image is at infinity? All right. What about object...
Wait, but is that... I gotta ask, is this always true? Like, when the object distance is infinity, is the image distance always at the focal length?
Correct. It's always true.
Oh, okay. All right, that makes more sense then.
Mm-hmm. When the object distance is greater than 2 times the focal length, right? The image distance is between the focal length and 2 times the focal length. Now, when the object distance is between the focal length and 2 times the focal length, the image distance is greater than twice the focal length.
Okay. I think I need to just sit on this.
Here, let me do...
Because this just seems like a lot. I see your pattern and that helps, but I really do think I need to sit on this. I don't know. Like, I'm looking at like the M greater than 0 upright. Like, I don't.
And wait, greater than 0. Wait, what's that?
M greater than 0 upright.
Oh, is he looking at magnification or something?
Yes.
Oh yeah. So, I was just going to write like if something is at infinity, other is at focal length. If
that helps.
greater than 2f, other is between focal length and 2 times focal length. By the way, 2 times focal length is a radius of curvature.
2f is the radius of curvature.
Mm-hmm.
Oh, wait. I do have that somewhere. Don't I? This was like the most brutal video to watch, too. It was like 40 minutes.
Yeah. So.
And it was weird.
So do you see what I wrote now?
If something is equal to infinity, okay, that's a nice trend, actually.
So basically, if the object is infinity, the image is at focal length. If the image is at infinity, object is at focal length.
Okay.
If the
better.
If the object is at 2 times the focal length, the other thing, the image, will be between focal length and 2 times focal length. If the image is greater than 2f, then the object will be between the focal length and 2f.
So this helps memorize this, and then you're just saying, like, memorize the image type it produces?
Oh, yeah. And then if the object distance is at 2f, the other will be at 2f. The image will be at 2f, and vice versa.
Okay. So...
Yeah. So basically, if an object gets closer and closer to that focal length, right, it'll produce a real image that gets larger and larger until that object is at the focal length, at which it'll produce no image, because an image at infinity is no image.
Okay.
Yeah. And now the last thing is, if the object is within the focal length, then the image will be really far, 2f, greater than 2f, on the opposite side. So that's when it's going to produce a virtual image. It'll be a larger upright virtual image.
Okay. So
it's
this
almost
is all
like,
good stuff.
Yeah, so it's almost like object distance and image distance are like sine and cosine. Because, sine of 0 is equal to cosine of 90. Sine of 30 is equal to cosine of 60. Sine of 45 is equal to cosine of 45, right?
So if I is greater than 0, it's real. I have to memorize these trends.
Yeah. Wait,
your
nothing about...
thing helps, but
yeah.
I still have to...
What were you saying about 0, though?
Look at this. About what?
0? Because for O, I mean object distance.
Oh, no, I know.
Okay.
I'm looking at, like, my own, like, thing where, like,
Got
I
it.
is greater than 0, like, what that means. No. Yeah, okay. So
I
think
see what you're saying. Yeah, if it's a negative number, it'll be virtual.
Yeah.
And
like, that stuff is kind of the stuff that I'm, like, I also have to memorize, obviously, because I don't really see another way, but that's okay. It's not too much.
Here, I just added another thing over here.
Probably put these in, like, Anki or something. I haven't been really good with Anki because the cards I made are, like, weird, so...
Okay.
It didn't help me that much.
Yeah, I just added another thing. It'll probably update in a sec, but...
Hold on. I have 2,000 tabs, so give me 1 sec.
Okay. So basically,
just got it.
Positive is real, negative is virtual.
For what is that? What is the letter there? R?
Oh, sorry, it just meant positive.
Oh, like to the left of the positive.
Oh, just if you get a value that's a positive, like if you're using like the thin lens equation or something.
Oh, a value. Oh, for I. A value for I.
Oh, yeah.
Okay.
For the image, yeah. If you're using the thin lens, like, yeah, if it's positive, it's going to be real. If it's negative, it's virtual, right?
Yes.
Mm-hmm.
F concave, like, all right, I'm good with this for now. This mirror stuff is gonna make my head explode right now.
I don't think I've seen like a question about the mirror stuff, but I guess it's good to.
Oh, seriously?
I mean, I just personally
It's
haven't
more
seen it. I
lenses?
usually see it with lenses because they're a lot more. Um, I don't know.
I
They come up
haven't
in lots of
seen.
things, like
I've seen a lot of
glasses and
lenses. Yeah, I
yeah,
guess
yeah.
I've seen a lot of lenses. Whatever.
And I usually just think of it as diverging or converging.
So I'm trying to think what other things like. Okay, so the couple other things that I wanted to go over, we can like prioritize so we're not here like forever. But
Sure.
I guess the Venturi effect is probably pretty quick, right?
Oh yeah. I usually I use like a straw wrapper, but to demonstrate that. But yeah, essentially what you have is
Straw wrapper?
yeah. I think I did it the other day with one of my other students, but um, I would use like a straw wrapper because it's light, and I would kind of like make this like kind of thing. Like I did this, like right, I don't know, something like this. That all right? That doesn't help. So okay, if you basically so
Oh
okay,
my gosh.
basically
Get rid of that. Actually, there's a couple things I did want to go over on here before my test tomorrow.
so if I had like a wrapper here, like that. Do you see that?
Okay.
And I blow down into that. What will happen to that, like the part that's like coming up? Will it go up or down?
Up.
It'll actually go
Right?
down.
What?
Because I'm blowing like underneath it, and that velocity of that air is going to go fast, creating a tiny vacuum, which lowers the
Wait.
pressure. Yeah.
I have no idea what's going on now. Honestly, like, I'm very confused. Let me pull up a picture of the Venturi effect.
Yeah, you're going to get like diagrams and stuff, but basically the idea is that if I blow, it works with a straw wrapper because it's more like light. But the idea is if I blow down in here, wait,
It goes down if you blow into it? How does that make any sense?
it goes down because when you blow into it, right, that like the air or whatever goes fast, and since it goes fast, it creates a tiny little vacuum underneath, which is lower in pressure, and so this thing will go down.
Fast.
It'll go down.
So I guess that's like one of the other things that I'm struggling with, I guess. Not so much related to the Venturi effects, because whoa. But pressure relationships.
Yes.
Like I was trying to write them out the other day. Oh my god, I have so many papers. And like I just want to go over all the pressure relationships. Like I get the Boyle's law.
Let me ask you this: if you double the diameter, what happens to the? What happens to the? Yeah.
Well, there was also something that I might have miswrote it when we were going over the other day, but like I looked at it again, like after our session, and so this is what I wrote, and I don't know if this is right or wrong. You increase blood osmolarity, so you have more salt in the blood and less water. Then I have water flows into the blood, which makes sense. So you're increasing your blood volume. And then I have increasing blood pressure, but wouldn't it be decreasing blood pressure?
No, because you have more volume, blood volume, right?
Yeah, so I thought
So it's gonna. There's more
volume and pressure have inverse relationship though.
So, well. Okay, so pressure is essentially like force over area, basically. But
I'm thinking about Boyle's law though.
mm-hmm. Oh, just think about like within the blood vessel, right? You just have a lot more stuff in it, so it presses against the walls of that blood vessel, producing a greater blood pressure.
That
Yeah.
does make sense, like when you put it like that, but then Boyle's law says that they have an inverse relationship. Pressure and volume.
Yeah.
So, like, is it just not true for the, like, I don't get that.
Well, that's used for like an ideal gas,
Is that why
and
Boyle's law is
blood's
just
an incompressible fluid.
Oh, okay, wait, that makes so much more sense. So this is just
So
for
you can
gas.
think like Bernoulli's equation.
Oh, I hate Bernoulli. That's kind of similar-ish to that. Okay. Yeah, the relationships with pressure just confused me.
Yeah. So if it was an ideal gas, for example, right? Then that means that if volume goes up, there's more space, right? So
Yeah, because I just did like the respiratory system the other day, so I like totally get Boyle's law.
Yeah, so in the respiratory system, right, when your diaphragm contracts, right, what happens to the volume, the like of your like lungs?
It increases.
Yeah, it increases, so there's a lot more like space for the gas to like do whatever it does.
Mess around.
And
Yeah, so there's
so the
less
partial
pressure.
is going to be less, and then compared to the outside partial pressure of oxygen, so you're going to inhale.
Yeah, I get that.
Yeah, so that works. Yeah, Boyle's law, that kind of Charles law, and whatever ideal gas law, essentially, like that all deals with gas, particularly ideal
I
gases.
didn't know that. Okay, that helps a lot. But then for fluid, it's the opposite.
So for fluid, especially an incompressible fluid, because the thing with gas is it's compressible, right? You can take gas and you can compress it like into, and like you can take gas, right? Let's just say it's like, I don't know, if you just had a balloon, maybe, I don't know, a balloon has gas inside of it, right? And you can compress that because the gas isn't taking up all of that volume. The gas is just, there's a lot of like, it just like, they're not really, you can compress a gas basically.
Okay.
Right?
I get that. Yeah.
So and that works like if you take like for instance like in a maybe a helium tank, right?
Yeah.
That's compressed like helium. Right? So if we like basically reduce that volume, like we make that helium tank smaller and smaller and smaller, the pressure inside of the gas that is exerting upon like against the walls of that
it's going to increase.
Yeah. So that's the inverse relationship with volume and pressure there.
Yes, I do get that. But I guess I guess if we could go over like, so for fluids, it's I guess the opposite, but also then like I was trying to figure it out. I don't know if there was a question or if I was just writing this down for fun, like cross-sectional area and like
Yeah. And
velocity
also one more
and
thing, blood volume is the volume of the blood, right? It's not the volume of the container. Because in what is it? In a gas, the volume is the volume of the container, of the thing
oh,
around it.
okay. Yeah, yeah, I see what you're saying.
Yeah.
Yeah,
So, yeah,
I
if your
can see
blood
that.
volume goes up, it's the volume of the liquid or of the blood, whatever, and it presses against, yeah, the container in that case is the blood vessel.
Oh,
Yeah. If you can think of like
but we don't
a
care about the blood
hemorrhage or
vessel.
something like that, or if you're bleeding profusely, you're losing blood, you're losing blood volume, so your blood pressure is going to drop.
Is there a
Mm-hmm.
Oh, that actually kind of helps. But is there an equation? Like I know the Boyle's law. Is there an equation for the relationship or no? Of the
There
fluid?
is like a flow rate, which is like equal to the, I think, like cardiac output times the heart rate, I believe.
What?
Yeah, cardiac output is equal to the heart rate times the stroke volume. Here,
Um.
I'll add it to your thing.
Oh,
Oops.
guy. Um. I feel like I do get a lot of this stuff on the list. Um. No, it is there.
Here, I added something. It's called the cardiac output. I don't know. It has this stupid guy person's face in it, but whatever.
Wait,
Yep. Mm-hmm.
never mind. Oh, sorry, random. Okay, wait. Okay, let's look. Oh yeah. Okay. Um. Cardiac output. So, yeah, this is probably not what I was thinking, but there's no like simpler equation then. Like,
No. Just because you're dealing with
that's fine.
volume, like you're dealing with, so like, yeah, for like ideal gas law and gases, since a gas is just going to be all over the place, right? It's not going to, like, you can compress a gas, but so the volume in ideal gas law and things like that have to do with the volume of the thing that contains that gas,
Yes, yes, yes.
and for
Okay.
like an incompressible like fluid, the volume is of that fluid itself.
Yeah,
It's
fluids are one of my
incompressible.
things that I need to look at again.
You know,
I
like a
haven't done that.
hydraulic press or something. You know, like a hydraulic kind of thing.
Yeah, it's been a minute since I
Yeah,
looked at
a
those.
hydraulic press works on that principle of an incompressible fluid. So like on one end, there's like you know, like you press down on it and it transfers that pressure down to the other end, and that's how like a hydraulic press works. That's why like hydraulic presses are so powerful. They can like, you know, they're extremely powerful.
So I get the relationship there. What about like velocity and area and stuff?
Mm-hmm.
Because I think when I was writing this out, like, is it all different between like gas and liquid? Like, I don't know. The pressure relationships are confusing me. And it's not exactly like a quick Google, like I tried.
Yeah. So okay. You said velocity.
Yeah, velocity.
Okay.
Because I have like V1, A1, but is that for just fluids then? Like, I don't really know.
Yeah. Because for a gas, it's not really just so okay. You can still treat gases as a fluid, and when that comes into play, you're dealing with fluid dynamics, which involve the Venturi effect. It involves Bernoulli. It involves Poiseuille. So that's a little different because generally speaking, with a gas, the velocity we think of as the velocity of the individual gas molecules, and so that if it's faster, right, it's going to be essentially like a measure of its temperature. Now
So,
compare that to if we treat the gas like a fluid, like in the Venturi effect. So like if the so that when I did that kind of like
oh
thing.
yeah, I still don't get the Venturi effect. I was just
So
like over it.
oh yeah, so just think about okay, so think about this or like that's kind of how a plane works, like an airplane. Because the airplane, like the wings of an airplane, are shaped in such a way, that when the airplane moves forward, right, it's going to basically like have it's shaped in such a way that it basically when the air hits the wing, it's going to go underneath it and create some turbulence.
Yeah, I remember doing this like
Mm-hmm.
in the beginning of my, like before my Kaplan class started. This was
Yeah.
like something we had to watch, but I don't really like the physics. I think that's the problem that I'm stressing out more is like I really don't know like any of the physics. I feel like and that's why I just write like optics and like random things on the thing because I
Yeah.
literally just don't know any of
Oh, all right. Let's see if I can
the
find a
physics.
better like.
But like I looked at it, but the physics for me is like harder to comprehend because I can't do this memorization of physics. It's like not really, it doesn't work like that. Um, but it also doesn't make sense, so I can't really put the concepts.
Yeah, I would. Man, I need like a really light. Maybe this will work.
Well, we can do that next time, and I can bring a straw wrapper.
Yeah. So basically, the idea is that so if something's shaped like that, and you're basically blowing air underneath it, that air has a velocity, which means it's traveling so fast that it creates a momentary vacuum underneath that straw wrapper. And so
Right,
underneath that straw wrapper, it creates that vacuum, which means it's a lower pressure, and that thing gets sucked down.
right. Yeah, that I think I'm gonna have to come back to,
Okay.
but I can come back to this pressure thing. Because I think I'm confusing a lot of different like. Actually, so we have this for volume. So the gas is not like a simple velocity, but then cross-sectional area
Yeah.
is like I know. So we just agreed that pressure is inversely proportional to velocity for a fluid.
Well, oh, for a fluid?
Yeah.
Yeah.
Did we do that? Or did I make that up?
No. Yeah. It's because basically at the point at which it's traveling faster, it's traveling like forward so fast that because all right, how about this?
Oh
Let's
wait,
yeah.
no. This is no, yeah. I actually know exactly what the question. I remember it now
Okay.
because I looked back at the question when I was
Mm-hmm.
like thinking about this the other day. Um, it was like a blood vessel and then it was like clogged. Okay, and that makes sense to me now because then if it's smaller, like the opening. Oh, but this is maybe area. If the area is smaller, then you're going to have a higher velocity. Oh, so this has absolutely nothing to do with pressure. It's velocity and area,
It kind of does
right?
because if the velocity is going faster, it's more streamlined. Like if you, I don't know if this is easy to notice, but if you like just turn on your faucet, it's like thick. When it leaves the faucet, it's like the same whatever
Yes, yes.
diameter of that faucet, and as it goes down, it gets thinner, like narrower.
So I get that the velocity and area are going to have an inverse relationship, but pressure has got to be direct with one and indirect with the other. Which one is it direct with?
So okay. The here. I told you about Wiki Pre-Med, right? They have
Oh yeah, I tried to like look at it the other day for something, and it said like invalid link or something like that.
Yeah, I think I noticed that too. I think they had a moment where they changed like the layout
and
or
now
something.
it's saying when I try to go on it, it's saying connection is not secure, and it won't let me go on it. So.
Yeah, okay. It seems like it's called integratedmcat.com now.
Oh,
But
okay.
they have this is like one of the best physics resources I've seen.
Okay, so I can look through this because physics is a little bit. Physics is where like honestly like. Whew. Um, but okay, so I guess we'll go through something. There's two things that I kind of wanted to go over before.
Yep.
Titration, like the equations and like all of that, like the titration and the and whatever
Yep.
that stuff is. It's like okay, we don't. I don't know. Whatever you think we have time for, the titration or the like the separation techniques things, like kind of just like the evaluating the experiments or whichever one I guess you think will be more helpful tomorrow, like when things will stay in like the chromatography stuff, I guess.
Mm-hmm.
And the gel electro, like when things will travel further or like
Yep.
stay on the solid phase or liquid phase, like that stuff like is kind of confusing to me.
Okay. So yeah, so basically yeah, so chromatography, they're all based on exploiting the affinity for something with a stationary phase compared to the mobile phase.
Yeah, so the difference between those also kind of confused me. I think
Mm-hmm.
the questions had to do with like which one would travel the fastest, like if it has a higher affinity to the stationary or the mobile,
Yeah.
like something like that.
Yeah, so if it has a higher affinity for the stationary phase, it's going to not move as fast.
Okay, so the stationary phase is what? It's like before you put the gel it, like
It's just the thing that is like stationary, like it's stuck. It's not moving. So like if it's like
on the bottom.
like if it's like a piece of paper, like that kind of chromatography, TLC, I forgot what it's called.
Yeah, the
That's
TLC, the thin layer stuff. It's on the bottom. Like it's the stuff like oh, it's the stuff before it moves, like before you put the gel in and run it,
mm-hmm.
kind of thing. Is that what it is?
Oh, I'm just thinking of like a very basic like you have a piece of paper and some solvent and you put like dots of the different whatever chemical things and then whatever has a higher affinity for the stationary phase, which is the paper in that case, as you know the water goes up and stuff, the thing
Yeah.
that has a higher affinity for the paper is not going to travel as quickly like upwards.
So will not elute
So
as fast.
the elute stuff then comes with like a column type of chromatography.
Oh, okay.
So
But then I guess it still wouldn't like elute as fast. It would just wouldn't move as fast or elute.
yeah, so kind of same principle with a column, right? Whatever's in that column is going to be the stationary phase, and So the thing that has the least affinity for that is going to elute first.
So the least affinity to and it also, if it has a higher affinity to the stationary phase, it won't travel as far. Is that true or false or not related or?
So that'll be true for like an example like the TLC kind of chromatography. For a chromatography column, you're going to essentially just differ. You're gonna try to separate just between two things. So like the thing that elutes first, right? Like if it's size exclusion chromatography, then there's going to be like particular like sized like pores in it, and the thing that can fit through those pores is going to elute first.
Um, okay,
And if it's like
so
a anion exchange or something, then it's going to attach to like
the
um
pot, then the
I
anion
always
exchange
mix
binds the
that up.
negative, right?
I
Yeah,
think
I
so.
mixed that up too. I gotta
So
look at
that's
that.
going to elute first,
Um,
and then for gas chromatography, it's you take something, you make it evaporate, go into the gaseous state. It's going to go through this thing with beads in it or whatever, and so the thing that has like the lowest atomic weight is going to take the longest to get to that gas phase.
wait, okay, so I have a question.
Yep.
Chromatography. So if you have like a column and your mobile phase has like the positive,
Mm-hmm. Wait,
like
stationary phase, like the
no, the mobile
beads.
phase is like the thing that moves, right?
Oh, so in this case, like for
Like the
column
thing that it binds
chromatography,
to or whatever.
yeah, the stationary phase is like the thing it binds to. Yeah.
Stationary phase. Oh no, I thought the mobile phase was what it binds to,
Mm-hmm.
not the stationary phase.
For column chromatography.
Just like in general, honestly.
Okay. Um. Well, for column chromatography, I believe. Yeah. No, the thing that's in the column is the stationary phase. The mobile phase is essentially just what you pour down through it that elutes.
Wait, this is like I think what I get confused on. I think I get so confused on which one is which. Like which I thought the stationary phase, and then you like pour the mobile phase in, and then if it's attracted to the mobile phase, like I
So
don't know. I
if
guess
it's
I'm
attracted to
confused.
the, yeah, so all of it's going to involve like separating something that has a higher affinity for the stationary phase. If it has a higher affinity for the stationary phase, then if it's a column, um, that's going to elute like last because it's wants to be with the thing that's stationary.
Wait, but what is this mobile phase thing?
Mobile phase
Like,
is just
is
the
it so for
solvent or
like
whatever.
if you're yeah, but then I guess that is what I'm saying then. So
Mm-hmm.
like for like the affinity chromatography, like
Mm-hmm.
the mobile phase is going to have the ligand that you want your protein of interest to bind to then, not the stationary phase, right? Like the mobile phase is going to be
So the mobile phase is just always. I mean, the mobile phase isn't that important because it's just whatever's there with the solvent. So just think about like if it's like a piece of paper, the mobile phase is like the water, and if it's a
wait, but I
column,
thought
yep.
so then which one like for affinity chromatography, you know how you have like things on the um whatever that you want it to bind to?
Mm-hmm.
Do you have things on the mobile phase or the stationary phase that you're looking for?
Oh, stationary. Wait. Sorry. Wait. The
I
thing with
think
the
I thought it
ligands
was
are
the
going to be in the
mobile.
mobile phase.
Yeah, so
Yeah.
that's what I'm saying, right?
Mm-hmm.
The stationary phase is like before you put anything in, and then the mobile phase, like if you want it to bind, then it binds to that. So if you have like um a positive thing
Mm-hmm.
on your stationary on your mobile phase, then the positive things will elute first then, right? Because they want to like get out of there.
Wait,
Or
you
will the
said
negative thing?
so the mobile phase is just going to be whatever solvent that you have something positive in, something negative in, something neutral in, or whatever. And
I
let's
thought
say
the
the
mobile
state,
phase we
yeah.
just said was not that. It was like what we wanted to like bind to.
Oh no, no. It'll That'll be the stationary phase.
Oh, I thought you just said that was the mobile phase.
Okay, sorry, my bad. I
I'm so confused now.
okay. So basically, like, um, see, I added some pictures in your thing. Maybe that'll kind of help out. The mobile phase is just essentially the solvent here. So, in a mobile phase, in like water, for instance, there could be a couple of ligands of what you're trying to like look at, and based on how great of an affinity it has to the stationary phase, it will take, if it has a higher affinity for the stationary phase, it'll take longer to elute. Or if it's, yeah.
So then I guess that's what I'm saying. So like if the stationary phase, say you're separating it out by like charge or whatever,
Mm-hmm.
if the stationary phase is positive,
Yeah.
um, then would the positive things elute first because they want to like get out of there, or would they?
Yeah, they'll elute first.
Yeah, right. Okay, so like if it doesn't, I guess then a lower affinity for the stationary phase would
Correct. Like the
elute
positive thing
first.
would have a lower affinity, right? For the stationary phase?
Yeah. So
Mm-hmm.
wait, I thought we said before though.
Mm-hmm.
We said before a higher affinity
Yeah.
would elute first.
No. Well, if it's a higher affinity for the stationary phase, it won't. The
Okay,
stationary
we have the
phase is
opposite from
always the
before.
thing that that
So a lower
will get
affinity for.
stuck.
Wait, I have to. I'm confused. Okay. A lower affinity for the stationary phase would elute
First.
and would not move as quickly. Wait, no, it
It
wouldn't.
it'll wait.
Oh yeah, that's the positive positive. Oh wait, it would elute first and it would move quicker, right? Okay, this is confusing. I will go over this. But yeah, all right, I think that's like the main stuff. Obviously, there's some other things I'm gonna want to go over.
Yeah, I
Um,
added some pictures in your notebook that
all
will
right, so I
hopefully
think
make it
that's like
a little bit
pretty
more.
much it for today, at least. But I'm taking my
Let's see.
practice test tomorrow.
Um, okay. There's a let's see, batteries, circuits.
Yeah, those.
Yep.
I'm like the batteries, like the galvanics and stuff. I can look at like the circuits I tried to look at today. I need some more background before I like start going into those. The fluid acid and base I'm fine with. I don't really know why I like wrote that. I guess I didn't know the difference at first.
Uh huh. I see electromagnetic
Moment,
waves, radio waves.
magnetic waves, electromagnetic waves. I don't even know what I mean by this. Um,
Maybe it was from some passage that you did about Doppler effects or something.
I don't know. Like this is definitely something that I'm gonna want to spend more time on though. I'm kind of getting like tired. So
Yeah. Yeah.
do you want to maybe I want to say I want to meet Sunday, but then like I'm probably gonna want to go over my practice test before I do this.
Mm-hmm.
So I guess I'll email or text you tomorrow, like letting you know how I do on the practice test, and then I'll try to have my practice test honestly ideally like went through before I do my research next week on Tuesday. So
Which practice test is this that you're going to do?
it's a Kaplan test.
Okay. I just want to see like, if you understand, like, certain things before you take it.
Sure.
Like, I mean, like, I'll just charge you for the 2 hours. I can do, like, a couple more minutes, though. Like, quickly, like, about parallel series, yeah, like, that kind of stuff. Like,
Yeah, so yeah, the thing was like I started looking through them today, but I think I needed more background for them. I'll be completely honest, because I know like when this was this I wrote
mm-hmm,
for like the passages that we were like kind of unsure about.
mm-hmm.
Um, yeah.
Um, so, in general, just, resistance, capacitance, voltage, circuits, parallel series, like, what do you, like, what about that stuff?
I know like the Ohm's law, the parallel and series, I'll be completely honest, like
Uh-huh.
um sometimes like 50% of the time I would say I have a hard time like determining which is which. Like I'm pretty sure the parallel is like the series is when there's like only one path, I would like to
Correct.
say. But then sometimes it's hard for me to figure out if there's one path. But
Uh-huh.
series I would say there's only one path.
Yeah, if there's any junction, like, in which the wire has to split in directions, that will be parallel.
Yeah, so it's that like I kind of get that. It's just more like I need to like practice, I guess, just identifying that. I know there's like a bunch of different equations for all of them.
Yeah, I mean, they're kind of, I mean, like, in series resistors, you just add them, and if it's in parallel, you add the reciprocals of it. But in other words, and I think I added it in the formulas thing. Let's see. Yeah, at the bottom of the formulas thing, I kind of wrote them out, um, and I wrote like an easier way of using it.
In
It'll be, yeah, under formulas.
formulas.
Yeah,
Okay. Yes.
on the bottom of it. So I just wrote out any reciprocal sums. So the
Oh yeah, you
thin
did
lens
write it.
equation is there too. But
Wait, on the
yeah.
bottom I see it, but I think like when I was looking at this, like I was just confused which is which, like parallel. Like I don't know.
Oh, okay. So check this out. So resistance itself, right? It's so okay. Think about this. Like, you're like, electricity is just electron flow through a wire, right?
Yes.
And so imagine you're an electron and you're going through a wire. As you go through the wire, there's going to be atoms of copper, if it's a copper wire, that get in your way, essentially. Like, you brush across them, and that creates friction, and that's what resistance is. So, let me ask you this. If that wire was really, really long, right?
Wait,
Yep.
you're saying it's gonna hit copper atoms?
Yeah. If it, usually a wire is made out of, like, copper.
Okay, so and that's gonna make okay, that makes sense to me.
So, okay, if it's really long, right, you're going to brush past a lot more copper atoms, right?
Hmm.
So the length of the wire is proportional to resistance. If it's longer, you're going to encounter more resistance. Now, what if
And that's
it's
just in general, you're saying like it doesn't matter series or parallel.
correct? But I'm gonna connect it to series and parallel. Now, what about if
Okay.
the cross sectional area of that wire is higher?
Then it would probably be lower
Yeah, because
resistance.
there's more paths for you to travel through, right? Now, in series, right? If you add resistors in series, you're essentially just making, like, let's say you have 2 or 3 resistors in series, it's basically one resistor that's just really long.
A huge one, yeah.
So that resistance is gonna go up, right?
Mm-hmm.
Alright, now if you're adding resistors in parallel, you're essentially creating one resistor that's just really, really wide. So that resistance should go up or down.
I don't get how you're creating a wide resistor.
Oh, because since, like, so 2 resistors in parallel, right? It means that you can split the current to go through, like, either one or the other resistor. So if you combine those two, they're essentially just one really wide resistor. They won't, just like in series, they're just in a straight line. It makes it really long. If they're in parallel, like this, you're basically making one that's just really wide. When I say wide, I mean like the overall area, cross-sectional area, is larger.
Yeah, I don't fully understand that because I feel like if you have 2 resistors in parallel, there's like a junction somewhere,
Yep.
so
Exactly.
it wouldn't.
So
they're
there's
separate.
options.
I would feel like.
So that junction, so like let's say it's the current is like 1 amp, that junction will split it. So it basically just gives you more space essentially for those electrons to pass through. Like if you had Christmas lights that were in series and one broke, then everything will, like, everything after that.
Because it could flow somewhere else too.
Yeah,
is
path
what you're
of
saying?
least resistance, right?
So it could flow somewhere else too. So the current's not all gonna go through the same place.
Exactly. So just like if you have a really wide, like big cross-sectional area in a wire, the electrons don't have to just go in one narrow direction. They can go like, oh, there's an opening here, there's an opening here, there's an
So
opening
we're
here.
lowering the resistance.
Yeah. So that's why you'll have a reciprocal sum when you try to figure out the equivalent resistance of various resistors in parallel. So that's the equation that I drew out. And for a capacitor, right, it's like a similar kind of thing, where capacitance increases with, the area of the plates. So that's why you'll see a reciprocal sum for, adding up capacitors as well.
Yeah, the capacitance I have to look at again, but
Yeah.
I guess just the series and parallels, but that makes sense, I guess. The resistance makes a lot more sense, honestly, now. But there's still, I think maybe, even if I go over maybe a section or something on Sunday, and then maybe we can meet, I gotta, let's see how I do, I guess, on it, but if I do bad, I should probably go over it a little. Yeah, because there's a lot of topics I do want to go over that I'm struggling with by myself. So
titrant and analyte and equivalence point. So let's say you have
yeah, that question was it was more I know what you're doing when you're titrating, but it was more of the equations and stuff involved with that, and
I don't remember any particular equation really. It's just that you're adding let's say the analyte is a base and the titrant is an acid, and you just basically add it, and the equivalence point is essentially when the moles of the base is equal to the moles of the acid.
Yeah, I'm gonna actually see if I can find this quick question later or when we meet next, because it was.
You can send me the questions through email, and I can answer them in the notebook, and I could do that before our session.
Yeah, I'll do that, because the question was how do you know if the acid or base was added or something like that based on the pH, and honestly I was what?
Oh, well, if the acid was added, then the pH should go down, right?
I'll try
Mhm.
and find the question because I could be like having it like that makes sense to me. So I feel like I hopefully wouldn't get it wrong if it was like that simple.
Mhm.
Like it was basically like a student did like an experiment. But I'll look for it. Um,
Okay. And then I see
so
some stuff about decay, like different types of radioactive decay.
oh yeah, that I need to spend like a year on.
uh,
It's
yeah.
gosh.
Um, I also made like a thread about that.
Oh yeah, I can actually look at that.
Yeah.
So I like don't really know how to use Reddit. That's the thing.
Yeah. It's
Um,
okay. I'll.
like, do
I
I
can.
search you or do you send like a link? Like, how does that work?
Here. Whoops. So wait. So what about that? Like, is it like Half Life or is it the different types of decay?
No, Half-Life, I feel like I kind of get.
Yeah.
Um, like Half-Life, I feel like is pretty straightforward, but it's more like uh, like I don't even know what I can't even say it because I don't even know what it's called. Something was emitted and then this was emitted and then what is happening? And I had no idea.
Is this
Okay,
based on a question about smoke detectors?
no.
Okay.
Wait, let me see. Um, this like might be wait, it's nuclear decay stuff. Let's see. Alpha decay, like positrons being released and stuff.
Yeah, yeah. Yeah, I gave you like two of these posts. Um,
And they're both for this. Okay.
oh yeah, they're both basically,
Let me
just going
copy
over
these
radioactivity and stuff.
links. That and this link. Okay.
Yeah. So
Yeah.
basically, like I write generally speaking, um, well, I mean, like most things should have a 1-to-1 ratio of neutrons and protons,
Yeah.
and if it doesn't, it'll decay to achieve that, right? So,
Well, I thought if
yep.
it doesn't, it's an isotope.
Well, yeah, and that's why you have radioactive isotopes, right?
Okay.
Like carbon 14, right?
Mm-hmm.
That's an isotope, and what? It's supposed to have. It has 12 protons, right? How many neutrons does it have?
Um, 8.
Um, wait. What am I?
What
Wait, am I wrong? Is it? No, I'm sorry. Wait, it's sorry. Carbon has 6 protons. It's supposed to have 6 neutrons for carbon 12, right?
Yeah, but for 14, it should have 8, right?
8 neutrons, right? So it has two
Yeah.
extra neutrons, right?
Mhm.
So that means it's neutron rich, and so it's going to get rid of those 2 extra neutrons. So a neutron will basically break apart into, because a neutron is essentially a proton and a electron, essentially, right?
A neutron? I didn't know that.
Oh yeah, proton and a neutron.
And an electron?
Oh, sorry. The neutron, yeah, will break apart into a proton. I say a beta minus particle, which is essentially like an
Wait,
electron.
which post are you on?
Radioactive decay. Oh, the first one.
The Okay, I think I'm on the first link. Yeah, let me just really quick. Yeah, I'm on the first link. Okay.
Yeah. So basically, everything wants a 1-1 ratio. So if you have an isotope, it's going to do something in order to return to that 1-1 ratio. So they can carbon date things, right?
Um, okay, yeah, I guess it's just like the when it emits like a helium nucleus, like I don't really know what that means.
Oh
So
yeah,
that's what I was
alpha.
more.
So that happens for really heavy isotopes like uranium, and it essentially emits an alpha particle, which is a helium nucleus. So a charge of 2 and weight of 4.
Um.
So yeah, so this kind of like make it like the trick for this is like to think about how.
Oh, so you subtract the 2 and the 4.
Oh yeah, I go into that in that second approach or in the second
Okay.
thing where I draw like how to do like the whatever. Like alpha decay means your element's atomic number goes to the left two places. Beta minus decay means that your element's atomic number goes to the right one place. Then beta positive, which
Wait,
is
where?
that's going to be in the part 2.
The second post. Okay.
But basically, the thing to think about here is just that, a neutron is essentially a proton and an electron. So,
Yeah,
there's something called
I
a
guess.
neutron star, which is like the densest type of thing that exists, and it's essentially
Yeah.
formed by a star that whose gravity is so powerful, it takes an atom, a regular atom, right, and it takes the electrons in that atom and it crushes it. So so the electrons and the protons are crushed together to fuse to form a neutron. And a
Okay.
neutron is the most is the it's essentially the hardest substance in the universe.
I definitely did not know that.
Yeah, a neutron star is like the size of Manhattan, but like the essentially like with the weight of like a star.
Okay, so I guess I should look through, like, I'm gonna look at your Reddits later.
Yep.
But then if we can meet, obviously, I'm probably gonna need to meet like maybe twice next week because just to go over my exam, there's definitely gonna be like passages and stuff I'm gonna want to go over.
Yeah.
And then also I have like a new list of topics. Some of these like are easy, like I can easily do on my own, but some of them I've been struggling with on my own. And some of them we went over today. So maybe we can meet like 2 separate times next week, one for like the test and one for this stuff.
Yep, of course. And you can, send me things in between and I can do them in the notebook.
Yeah, I'm gonna go look for those, if not today, tomorrow. I'm gonna look for those the question, although I don't even know how I'm gonna find it. But I'm gonna try and look for like the one about the titrant thing. Because I thought there was like an equation that I was like, I just have no idea where this is coming from.
Mm-hmm.
But I'll send you that.
All right. And you saw the thing that I added on pathogens? Like my handwritten notes that I scanned?
Oh, I think I did.
Like
yeah, the new...
On prokaryotes and viruses. And then I have some stuff on cells that I also added. Oh, and then... Oh, yeah, there's all this stuff that I just noticed on microtubules and stuff.
In here. Okay, wait.
Yeah.
Wait, oh my god, wait, it goes over. Holy crap, I have to zoom out. I didn't see how many pictures. I only saw this first picture.
Mm-hmm.
Oh my god, wait, there's so many pictures. Okay, wow. No, I only saw the first one, honestly, but...
Yeah, this is from my notes from when I was studying for the MCAT, and I use lots of different sources to get the correct information, and so that's what this is. So I guess I write microtubule made of tubulin, hollow-like structure with alternating alpha tubulin. All right, don't need to know that part. They grow from MTOCs, i.e. centrosome, kinetochore, centrioles. They're responsible for the movement of vesicles, formation of the spindle, flagella, chromosome movement, cilia. When it comes to cilia, there's different types. There's some in the respiratory tract. There's some in the fallopian tubes.
Wait, what picture are you looking at, though?
Oh, yeah. So some of these are side by side. So
Oh my God. I keep like
Yeah,
not
I have a bunch of stuff on the cell as well.
Yeah, I was looking at I was doing the kidney today. I was looking at your kidney slides. Those were pretty helpful.
Oh yeah.
Um, yeah, I was looking at that. That actually helped me a lot.
Oh,
Because
that's good.
the videos of the kidney are not very helpful. Like the
Mm-hmm.
videos are the book, I guess. I was trying just from the book,
Yeah.
and that didn't help me at all. Um, oh yeah, now I see where you were. Okay, cool. Yeah, I'll look in this. Perfect. All right, so I guess I'll text you because, but then it's weird because sometimes my phone's off. I'll let you know tomorrow how the test goes, and then we'll plan a day to go over. Maybe Sunday I'll go over the test earlier, and then if I have like passages, we can go over that, or we can just do the like some of this content stuff.
Mm-hmm. Yeah, and just
Yeah.
feel free to send me particular questions and stuff like pass it from your test, or if you can
Yeah, because I
find that
feel like I
patient
need to move
one.
my test like back already, but like I feel like that's like a little like early to
When
be
was it
saying that.
scheduled for again?
September 10th.
Okay.
So I have like time, but like not that much. I don't know. I feel like what I was doing the last like month just wasn't really working and didn't help me at all. Like the way I was studying with the Kaplan class, I
Mm-hmm.
hated.
Yeah.
So
Okay. So yeah.
like I had the time. I'm not
Huh?
applying till next cycle, so I had the time to push it back if I
Yeah,
needed.
you have time till June, I suppose, right?
Yeah, exactly. But like I have this summer now to study, and like
Mm-hmm.
it's gonna be harder to study when I'm like doing my internship and like have
Mm-hmm.
5 classes and stuff. So
Yeah. You can like I took the test like 3 times, so maybe like if you feel like you're ready like in September or whatever, you can take it and then see how you do, and then if you want to do better, you can like it's going to be harder to study when you're in the midst of all your internships and stuff, but you've
mhm.
already like studied enough to like take it in September, so you don't have to study with that much like intensity if you're gonna like maybe
Yeah,
schedule it
I
again for like the summer, June or something. I don't know.
I'm really gonna try to like keep it for September. Like I'm gonna try to keep it for September,
Yeah,
obviously.
I just mean
But
like
like
for like your first time, if you want to like retake or whatever.
yeah,
I don't want that to be like a negative attitude, but like people do that all the time.
yeah, no, I totally hear that, but I know it's gonna be like harder to study the second time because I'm like even like all the tests. I don't know. I've just heard like some of my friends who've done it who just said it was like harder because then like they kind of remember the tests when they were taking them, so
Yeah.
like they have no idea if they're actually going up and stuff.
Oh,
Um,
you mean like the practice tests that they take? Yeah. But there's so
yeah,
many
like the
practice tests.
materials
Like
aren't
there's
as like
like the next step ones which are really good. There's the Altius ones. So there's a lot
yeah,
of material out
but
there.
just because I feel like I do still have so many content holes because I didn't like study correctly first. But I don't know. I guess we'll see if I have time to like catch those up in time.
Mm-hmm. Okay. So yeah, send me questions and stuff. I'll answer them in the notebook, and
Yeah, I'm gonna look for. I gotta find that Citroen one. But yeah, so I guess we'll meet twice, at least probably next week. And I'll stay in touch with how that test went.
yeah, I'm looking at content to Roman numeral 2 galvanic cells. I talk about that there, like when you said you wanted to go over like batteries. And then
Yeah, no,
underneath,
your galvanic cells you actually went over with me once, and then we did it after in the Kaplan course, but the Kaplan course confused me a bit when we went over it. I don't remember exactly why.
yeah, I'm just looking underneath it, and it seems like I also talked about the law of mass action, which I went over today. But so there's that, and I have an example And then I also have some stuff that I wrote about um, blood volume and blood pressure.
Oh, I was actually trying to look at this the other day, the blood volume, when I was like trying to figure this out by myself, but I was a
Mm-hmm.
little confused. So I just like was figured I'd just ask you about it. What did
Yeah.
I use today? I used some of your physics something today. I forget which one it was.
Mm-hmm.
Um, yeah, I don't know. This like just confused me, so it was like very random.
Yeah. In the blood volume thing, that's in the galvanic cells thing and the content 2 Roman numeral 2. I go
Yeah.
into it pretty, like, like, uh, precisely because a lot of times people just they don't care about the blood volume aspect. They just want blood pressure. Um, and so I talk about basically like how, like, for instance, like in whatever in this entire process, right? You can have vasoconstriction, right, which can cause an increase in blood pressure, but not an increase in blood volume. And then I have, like, for instance, like that's like what angiotensin 2 does. And then I have aldosterone, which causes the reabsorption of salts, which causes
Yeah.
water, and that increases blood volume, which
I
also,
think this
yep.
is like what confused me is where are you seeing like the
um
vasoconstriction thing?
oh, so content 2 galvanic cells, it's
Yeah,
on the
yeah,
bottom of
yeah.
that.
I
Oh, you
see
see
like
it?
the I see the diagram,
Yeah.
but oh, vaso on the bottom is
Oh, yeah, yeah.
vasoconstriction.
Yeah. So basically, what, like, blood pressure drops or blood volume drops, right? Could be due to dehydration. Uh,
The blood pressure or volume
I
drops
talk
though.
about both of them. So, like, for instance,
But it's
right?
not both, or it's one or the other you said before.
Wait. Oh. So, well, in red, I write like dehydration, which will cause a drop in blood volume, which will cause a drop in blood pressure.
Oh, yeah, okay.
Because, like, because, like, blood pressure can go up and down depending on like, constriction and vasodilation. But blood pressure can also go up and down depending on blood volume. So I wanted to differentiate between the two. Yeah. So, I write like it'll be detected by, either the arterial baroreceptors, and basically I go into like different, like, things that can happen.
Okay. Yeah, I'm definitely gonna like study. I'm gonna review some of the psych social terms before I go to bed tonight, so I like have those fresh in my head because I honestly don't really like review psych social probably as much as I should. Um,
Oh yeah, that stuff is a lot of, like, content
like
stuff.
yeah,
I went over that a couple of, like, passages with my other student. She also was doing Kaplan, so yeah, if you wanted to ever go over that stuff, we can do that too.
yeah. I mean that stuff is I feel like more like self-explanatory. And so
Mm-hmm.
I don't go over it as much. But then like when I get them wrong, that's like when I start going over the terms.
Yeah.
Um, except for like obviously like the eye and the ear and the brain and that stuff. That's like you gotta know. It's not self-explanatory.
Mm-hmm. Yeah. With the
Um,
eye and the ear, like, or rather just the eye part, that's where, like, the lenses kind of thing comes in. Because remember when we talked about glasses?
yeah,
That's also in the optics Reddit link that I sent you. Because that can kind of help you.
yeah,
Because I draw, like, the type of lenses for glasses, and, like, converging will be like, convex, diverging will be like concave. And then if you know that, then if it's a mirror, you would just know it would be the other way around.
yeah. I'm gonna look through your Reddits and then I'm gonna do some psych soc
And then
and then I'll take my test.
for the ear, like, in the external auditory canal, it's like sound traveling through air, right? And then in the middle ear, it goes through the ossicles, the bones, so it goes through like a solid. And then in the inner ear, it goes through the endolymph. So what happens to the
Liquid.
speed of sound in those three areas?
Well, the air, speed of sound in air.
Mm-hmm.
And then in the solid, I'm going to say it's going to slow down.
So that would be true if it was like light, but since sound, right, it's just vibrations.
Yeah.
So sound actually travels fastest in a solid.
Hmm. And then faster in air or liquid?
What do you think?
I want to say air,
Mm-hmm.
but I think it's going to be liquid.
So why do you think it'll be liquid? If it's
So I
fastest
want
in
to
a
say air.
solid, right? The closest thing to a solid, what would that be?
It's the liquid.
Mm-hmm.
It's the liquid. That's why.
Yeah, and that's just because it's based on vibrations, right? Like sound needs a medium to
Hmm.
travel through, but light is the opposite. Like light's fastest in a vacuum when it doesn't have a medium, but when it enters a medium, it gets slower. So
Hmm.
sound is like the opposite. Sound requires a medium.
Got it. All right.
Yeah. So yeah, you can send me an email of questions. Oh, and then you can send it to me of like the other subjects or whatever that you like wrote down.
Yeah, I'm gonna like go through them because some of them, like, honestly, like I just need to do by myself, but a lot of it is like physics that like just like the concepts
Yeah.
behind the physics.
Yeah.
Um, because like I think I'm looking at physics on like more of a microscopic level, and I need to like understand what's going on because that's why like when I'm looking at it later, I have no idea what it is because I
Mm-hmm.
don't really understand it.
Yeah. Yeah, the concept, yeah, like the if you have a conceptual understanding of the physics, you're going to be like awesome. You're going to do well on everything. Like
Yeah. And I think that's like where I'm really lacking that. So that's
yeah.
why most of these are just like things from the physics that I'm like, what is
Yeah,
going
cuz
on?
most people if they just rely on the formulas, they don't necessarily know like when that becomes relevant, like when you're talking about fluids and the ideal gas law and like how
Yeah,
pressure
see, like
and yeah.
that's my problem is because like then I'm using like the fluid equation for like the
Yeah.
gas.
Yeah,
So
yeah.
it doesn't like that's why I was like, oh, like is this wrong? And it was like not wrong at all. Like I was like, oh, the blood pressure.
Mhm.
Um yeah, so that's why I want to go over like the physics. So I guess we can pick a day to do that next week.
Yeah. But yeah, send me an email with, all those topics and stuff, okay?
Yeah, I'm gonna go through them later and I'll do that.
Okay. All right then.
Great. Thank you.
Yep, no problem. Have a good one.
Have a good night.
Thanks.